Continuous emissions monitoring systems, or CEMS, have come a long way since Congress first articulated performance standards for new stationary sources back in the 70s. Power producers, as well as keepers of other industrial-scale combustion processes in the U.S., must continually measure and report the output of nitrogen and sulfur oxides, carbon monoxide, and other potentially harmful byproducts. And today, they have at their disposal a range of solutions for doing so. Hello, this is Keith Larson, editor of Control Magazine and ControlGlobal.com. Welcome to this Solution Spotlight episode of our Control Amplified podcast, sponsored today by SICK. With me today to talk about the range of CEMS technologies now available and how to choose among them are Phil Zyskowski, Market Application Engineer, and John Calame, Market Product Manager for Analyzers and Continuous Gas Analyzer Systems, both with SICK. Welcome, Phil and John. A real pleasure to have you join me here today.
Thanks for inviting us.
Keith.
You bet.
It's an exciting topic. So
very, very relevant in this day, that's for sure. Maybe start off with you, Phil. SICK has obviously been in the CEMS and gas analysis business for decades and now offers a full breadth of solutions. Perhaps we can start. You can start us off with a bit of historical perspective on the first analyzer systems used for CEMS reporting and how those options have evolved over time.
Sure, and it's a history we're proud of, and so I'll try to keep it short and simple. But it has to do with our funny name, SICK, and it's actually a family name. And the founder, Dr. Irwin SICK, was an inventor, and in particular with optics and light. And they were fascinated and drawn to finding solutions, and it's always been safety or environmentally focused, right? And so the story goes where he started his first shop, a very simple shop, was a low rent property near the airport in the town that he started the business in, right? And he was fascinated by the beacon that indicated the position of the airport and the runways, and he saw how that light from that beacon broke up on foggy days versus clear nights and rainy days. And so that's really where he got the idea for our first CEMS monitor, and that was for measuring dust. Mm-hmm. There's concerns with the industrial revolution going on at that time and all the pollution. And so he used an optical system, a very simple but brilliant system to measure dust, and that evolved into measuring gases as well. And so he got to a position where really, if it wasn't something he could invent, he was smart enough to acquire. And so when you talk about that history, Keith, evolving over time, we simple infrared-based systems, which we'll talk about later, cold, dry, for measuring CO, CO2, anything that's infrared active. And then the evolution of techniques like ultraviolet to look at things like ammonia and SO2. And it's gone step by step in different directions, but for sure, we'll talk about the full portfolio, through the process of these questions and interviews. But it's been tough to keep up with the times, and so part of that, is how the regulations. The question you asked me was CEMS reporting, right? And so the regulations have evolved over the time as well, and probably we'll get into it a little bit later. But things like measuring ammonia. Ammonia has been injected by a lot of our power plants, for example, and it was cheap, it was easy to inject, but now the concern is ammonia slip. How much of it are we over-injecting, and how much is ending up in our fly ash at the end of the day? So those are evolutions that we had to keep in step with.
Yeah, and as I recall, SICK was a real pioneer around safety systems as well, with some machine protective monitoring, also using light as well back in the day. Yeah, it's referred to as a safety curtain. Yes.
So it's really, to keep workers, hands and body parts out of stamping machines.
Yeah.
And, with Homeland Security, that those products have taken off for us as well. Different subject for a different time, but there's more than just the safety aspect for it. It's identifying where people are at the right place or the wrong place. And it's interesting.
Yeah, well, we'll leave the pattern recognition assisted by AI algorithms for another day. That's all.
Yeah, we don't have enough time. We don't have enough time for that.
Yeah, but maybe John, you could talk a little bit. I know there's some different requirements? I mean, obviously the big users traditionally around the world is the power industry. They were really the first required to monitor their emissions. But are there different requirements for some solutions if you're talking about power gen versus, say, chemicals or refining or other process industries that may need some sort of a monitoring solution?
Yeah, great question, Keith. Yeah, the power generators were the first ones to be hit with the Clean Air Act, and typically when you think of power plants, I think of coal power. There's also gas-fired power, but all of them typically require general purpose analyzers. When you move into chemical, petrochemical, and refining industry spaces, different regulations, different hazardous area electrical requirements, and usually a minimum of Class 1, FM Class 1 Div 2, or in some instances, Class 1 Div 1. So from our standpoint, from a supplier standpoint, we have to comply with the electrical area classification. And so it's a little more trickier, but we have the solutions for Class 1 Div 2 to either in a purged enclosure or a non-incentive type arrangement to be safe in those areas.
I understand there's also significant differences around the types of some solutions, whether they're extractive or increasingly moving more towards kind of probe-based systems that are in situ or in place. Maybe you could talk a little bit, Phil, about maybe in the context of the installed base globally, are there different types of CEMS systems that are prevalent in different regions around the world, and which kinds? Just kind of give us a sense, because I know obviously SICK had its roots in Germany and in the European market originally, but have they really, through the different regulations, kind of evolved differently around the world?
Yeah, they have, and it's interesting because regulation-wise, there's a lot of countries, and again, let's talk regulations and not analyzer solutions.
Sure.
Or systems, but a lot of countries will make reference to US EPA standards. And Germany does not, but the Saudis, Mexico, Canada, to name a few, China also typically references the standards that the US EPA has set up. And so you would think that makes everything cookie cutter, and it's actually actually not. It's in most of Europe, the attraction early on to an in situ measurement, and it's a strange word we don't use at the kitchen table every day. So it's probably Latin based for inside of, right? So in situ means we don't extract the sample and pull it somewhere and chill it and filter it and then put it through an analyzer like maybe you would do in a laboratory. In situ means we stick as much of the analytical measuring cell inside the stack or ductwork that's being measured. Mm-hmm. And so that is typical outside of the U.S. as a SIM system. And in the U.S. market, they chose to adapt a more complicated, typically, and as John mentioned, most of this burden fell on the coal-fired power generation industry right off the bat. But so they use a more complicated dilution extractive system that pulls the sample down from the middle of the stack into a shelter down at the base of the stack and goes through a series of filters and chillers, and it takes some time. So there's always a risk there of changing your sample between point A and point B. Maybe some of the constituents get entrained in the water vapor and they get dropped out. So always our approach has been to go in situ unless we can't make in situ work. Right. And of course, the next trick there is to meet the regulations that were adapted for the extractive systems. And so we've done several modifications so we can adapt to the U.S. market.
Yeah. One of the things that maybe be good to clarify on, obviously, the regulations requirements for being exposed to a calibration gas directly. How do you go about doing that in a in situ probe base? You're not filling that stack up with a calibration gas. That could get pretty pricey on a regular basis. How does that work?
Well, good for the gas calibration folks, right? So there's two approaches, and it kind of goes back to your earlier question about power generation versus some of the other industries, right? And so power generation has got the strictest calibration requirements, and typically it's called Part 75, and that requires a daily gas calibration. That is written in the rule, and so we adapted our regular or in situ probe to have an encapsulated filter. And it's a sintered metallic filter that allows us to send the calibration gas into the probe space, the little measuring section of the probe, and pressurize it with your calibration gas. And it exposes the cal gas to the receiver, and it also forces the stacked gas out, so you get a nice clean calibration standard. But in the other industries, we've incorporated, and it's in all of our in situ analyzers, a series of internal optical filters. And so Part 60, for example, so it's an EPA regulation as well, but it does allow the use of the manufacturer's suggested optical calibration filters as your daily calibration. So you do not have to use calibration gas on a daily basis. You've got to check the analyzer on a quarterly basis still with calibration standards, but so there's savings there for sure, and a lot less maintenance if you can get by with just using the optical filters.
Makes a lot of sense, really does. What other factors need to be considered when end user needs to select a system? What do they have to consider? Because obviously there's even on the extractive, there's the cold dry systems that drop the water out by dropping the temperature of the sample. But then there's also hot and wet systems, and then there's the probe-based systems, the in situ options. What are the considerations that people really need to look at when deciding between those technologies or those general approaches?
Yeah, I mean, I'll ask John to chime in a little bit, but I think our approach always at SIC from a applications evaluation point of view is always to try in situ first. And so there will be showstoppers, we call them, that will rule in situ out. One of them may be access, where the customer wants to take a sample. There's just not enough room. So an extractive probe might be the size of a shoebox, whereas our in situ analyzer, it's 5 times that. So you may not have room in that particular area to install or withdraw. At some point, you're going to want to withdraw it, right? Our next approach is always hot-wet. After that, hot-wet, it's a special, unique construction that we've invented that allows us to take the sample in without having to put it through a chiller. Okay. And so that eliminates a couple extra pieces that are usually maintenance intensive, right? Water coalescers or chillers that have pumps and filters and things like that. Yeah. And then, finally, if neither of those two approaches will work, then we have the cold dry, which is tried and true. There's familiarity with that, and so that's the way to go. Sometimes, Keith, it's the measurement gases that drive that as well. Typically for CEMS, though, we have an in situ solution for all that, but if the customer wants to measure something more exotic, we may have to go with a cold dry analyzer that has more options for gas analysis. Gotcha.
So that's beyond the UV or IR type of
yeah.
Analysis.
Yeah. Yeah. And it depends on how much room is there too. We had talked about some changes happening, and John mentioned gas-fired plants coming on board. I've even got some of my customers converting part of their coal-fired plants to run on natural gas as a fuel. And so depending on what they have there already in the way of real estate, in situ is also often a nice surprise. They don't need a lot of extra hardware. They don't need a lot of extra, elevators and things. It could be installed somewhere that's handy to get at rather than up on a stack somewhere.
Yeah, no, that makes sense. But given you mentioned this is a pretty dynamic trends in this industry. Given the increasing pressure on industry to account for and reduce greenhouse gas emissions, it seems reporting on carbon dioxide and other greenhouse gases could be in our future from a regulatory standpoint, or just from companies that want to have more complete reporting to their stockholders, those kind of things. Are there any of these solutions that are more particularly suited or more flexible to adding new analyses to the mix? Say you've already got something installed. What's involved if you wanted to add another component that you didn't have part of the original mix?
Yeah, for in situ, for us, it would be a separate analyzer, so they have to make a separate penetration for a single probe or a cross duct for measuring CO2. If it was extractive, say a cold dry, it would just be a matter of adding an additional optical bench in DIR, or we may be able to modify change the calibration on the existing NDIR that's already in place. So, just off the top of my head, Phil, you may say different, but I would think, the extractive might lend itself to be modified to, if it's after the fact. I mean, if we know about it going in, of course, we can plan for it and design it, but if it wants to be added in the future, I think it's a little easier to add it with the extractive. Phil, do you agree or disagree?
Yeah. I mean, the thing to consider also, John and Keith, is the numbers, right? So typically with an in situ UV, we make the bench compact on purpose, and so we're typically limited to 3 measurement components there, right? And with the new generation, we've made the optical bench a module. So if you change your mind and say those aren't the 3 we want, there's a good chance that we can supply you with another optical bench module that would take some setup, and it could be done in the field. Whereas like a hot wet, you can pick from a list of 9 gases. Yeah. Right. And so like John said, if you kind of know ahead of time, we've got this ammonia slip thing coming up, or we've got, someone on the process side is interested in this. It's going to be our CEMS, but we would like to take that, that additional measurement. We could put it in and keep it turned off, or we could be there and running in the background, or there's a bunch of different options. And then for sure, the cold dry, it's a matter of a module pretty close to plug and play to add more gases. You just add another rack.
Yeah, I suppose if you're thinking ahead, you could have a extra process penetration already made, and do the same with adding another probe the other way around, I suppose.
Yeah, and that's part of what happens in the process when we start talking with customers. Is we try to enlighten them to what others have done, or what considerations other people have made, and in some cases open their eyes to, I didn't know that was possible, or that would be handy, especially on the front end, rather than having to turn things off and re-engineer them. So,
No, that makes a lot of sense. All other things being equal, I mean, as a chemical engineer, I always had the sense that an in situ measurement, because it's immediate and you're doing it at that actual time, and you're not pulling a sample out where things can go wrong and it can get corrupted somewhere along the way, that in situ is a better measurement in a lot of ways. And when it comes to, seems like an cost design and installation effort, also it's a more elegant solution in terms of the number of moving parts involved. Would you agree with that? And what sorts of savings are we talking about when it comes to initial capital costs and over the full system lifecycle? Have any users done a proper economic lifecycle comparison? I sense they probably have, but what have they found on the in situ versus extractive solution?
Yeah, Keith, we were at a EPRI conference, and one of the integrators did an analysis on in situ versus extractive, and over the 10-year life of the system, he came up with it was $1 million cheaper to do the in situ route versus extractive, and that's taken into account the initial cost, installation, capital costs, operating expenses, consumables over the entire 10-year lifespan of the system. So the cost savings, if they can go in situ, are extremely attractive over the life of the analyzer system.
Yeah, and there's nothing really holding back U.S. power generators or other organizations from using in situ in terms of the regulatory requirements. There's nothing that dictates which way they have to go. It's just kind of more the way they've gone. Is that fair to say?
Yeah, I mean, there's a comfort level. Right?
Yeah.
And so people are, and I get it. The cost of some of these systems, no one wants their name associated to a mistake, right? Oh my gosh, why did you pick that? Why didn't you just do the thing that we always did? Why did you try that? So there's a little bit of, anxiety over that. And I think that's up to us as a supplier to, prove, go above and beyond to build some comfort and prove that these work the way that they work as advertised. Right?
That's great. All right. Well, I think we're about up to the end of our time. Thanks so much, Phil and John. Really appreciate your sharing your perspective with us today. Again, my guests today have been Phil Zyskowski and John Calame, both of SICK Process Automation Technology Group. For those of you listening, thanks for tuning in, and thanks also to SICK for sponsoring this episode. My name again is Keith Larson, and you've been listening to a Control Amplified podcast. And if you've enjoyed this episode, you can subscribe at the iTunes Store and at Google Podcasts. Plus, you can find the full archive of past episodes at controlglobal.com. Thanks again, John and Phil, and signing off until next time.